Welcome to the explainer. Picture this. The alarms are blaring, a kick just entered the wellbore, and the driller successfully slammed the blowout preventer shut. You've contained the kick. Take a deep breath, right? Well, actually, here's the terrifying reality. A shut-in well is definitely not a safe well. You haven't killed it yet. You've literally just trapped it. So now you've got this highly pressurized bomb sitting 10,000 feet below you, just waiting to be disarmed. You've got to get that explosive gas out and heavy mud in without ever letting the well go wide open. Today, we're exploring exactly how that incredibly delicate disarming process happens.
Okay, let's dive right into this by establishing exactly what we're up against here. If you were to just open a valve on a shut-in well, you're going to get an uncontrolled pressure blast. The gas expands violently, blowing mud, rock, and hydrocarbons absolutely everywhere. I mean, it's a full-blown blowout. But if you route that flow through a tiny, adjustable restriction, you get a controlled, steady stream instead. You're bleeding the pressure off safely, just one careful turn at a time. This controlled bleed-off is literally the only way to swap out the light mud for heavy kill mud without dropping the bottom hole pressure.
All right, let's move right into Section 1, Anatomy of the Choke, dividing, restricting, and controlling flow.
So a choke manifold is basically a highly engineered arrangement of heavy piping and valves, which we call the chokes, used to circulate drilling mud while the BOP is closed. Now, it doesn't create flow or pressure on its own. It simply decides where the flow goes and how restricted it is. We can easily picture this using the classic garden hose analogy. Think about when you're out washing your car. It's the exact same volume of water coming from the tap. But if you put your thumb over the end of the hose to restrict the opening, the water suddenly shoots out way faster, and the pressure building up behind your thumb dramatically increases. That is exactly what a choke does to a well's returns. The tighter you squeeze that opening, the higher the pressure behind it.
The absolutely crucial point here is understanding this concept of back pressure. And honestly, this is something that catches new hands every single time, because it completely fights your human instincts. To increase the pressure holding the well in check, you close the choke. I know, it feels entirely backwards. You're closing a valve to raise the very pressure you're trying to control. But that deliberately increased back pressure is exactly what is holding the formation back. The choke isn't relieving the well, it's holding it.
Which brings us nicely to Section 2, the U-tube balancing act.
To really wrap our heads around this balance, imagine the well as a giant U-tube. One side is the drill pipe going down, the other side is the annulus coming back up. Your primary goal is to keep the pressure at the bottom of that U-tube just above formation pressure. If it drops too low, more gas comes in. If it spikes too high, you fracture the rock and lose the well entirely. As that gas bubble rises up the annulus, it expands. And when it expands, everything upstairs on the casing side changes. The pressure is going to swing wildly. The tool you use to hold the balance is the choke, and the gauge you watch to know if you're actually succeeding is the drill pipe pressure gauge. That's it. Hold the drill pipe pressure constant and the bottom hole pressure stays constant. That one single rule, it's the entire method for killing a well.
So, let's look at how we actually do this in Section 3, executing the well kill, a step-by-step procedure.
Right after you shut in, you immediately read the drill pipe and casing pressures. Next, you calculate your kill mud weight. Then the circulation begins. You start pumping that heavy mud down the string. And here is where the magic of the operation happens. The mud pump runs at a fixed, slow rate. The pump operator does nothing but hold that specific rate steady. Meanwhile, the choke operator is the one doing all the real finesse work, constantly adjusting that tiny restriction to maintain the right back pressure as the returns go out through the manifold, to the mud gas separator, and finally, straight to the flare.
To guide the choke operator, there are basically just two numbers that bracket the entire well kill. The first is the initial circulating pressure, or ICP. This is exactly what it takes to get the fluid moving. You just take your shut-in drill pipe pressure, your SIDP, and simply add the slow circulating rate pressure, or SCRP. This gives you the target pressure you need to hold on your drill pipe gauge the absolute second you start pumping the kill.
Next, we calculate the final circulating pressure, the FCP. This is your target once the heavy kill mud actually reaches the bit. You take your slow circulating rate pressure and multiply it by the ratio of your new kill mud weight to your original mud weight. So let's say your slow rate is 400 psi and you're raising mud weight from 12 to 13.2 pounds per gallon. The math is just 400 times 13.2 over 12, which gives you 440 psi. Between that initial pressure and this final pressure, you have safely bracketed the entire operation.
Next up is Section 4, Fighting Your Own Instincts, the Psychology of Pressure.
But look,
Executing this isn't just some clean math problem on a whiteboard. You're fighting extreme physical hazards to survive a well kill, and the primary hazards here are erosion and people. You've got gas and rock cuttings blasting through a tiny orifice at an incredibly high velocity. Honestly, think of it as the world's most aggressive sandblaster. This abrasive mix will cut through solid steel remarkably fast. A choke can easily wash out and erode away right in the middle of a kill operation. And that's exactly why absolutely nobody stands beside a live choke manifold or a high-pressure line under kill conditions. A washout there releases a jet of pressure that would easily cut straight through a human body.
Which is exactly why the manifold is over-engineered with redundant paths. You don't just have one choke. You have parallel adjustable chokes, manual backup chokes, and bypass runs for instant rerouting. If a choke washes out mid-kill, you don't panic. You simply manipulate the upstream and downstream valves to switch the flow to another path, without ever stopping the pump or losing control of the well. In this business, routing flexibility and redundancy are the exact same feature.
Now let's talk about the psychological battle, because here is the ultimate test that decides if a contained kick becomes a catastrophic blowout. Imagine you're running the choke. The gas bubble is rising up the annulus, and because the gas is rising, it's expanding, meaning the casing pressure on your console is absolutely skyrocketing. Your human instinct is screaming at you to open the choke and relieve that massive pressure before something explodes. So do you give in to your instinct and open the valve?
The answer is an emphatic, non-negotiable no. Rising casing pressure during a controlled kill is 100% normal and expected. Gas expands as it rises. If you panic and open that choke to relieve the casing pressure, your bottom hole pressure drops instantly below the formation pressure. The well is going to immediately take another kick, and you have just made your problem infinitely worse.
It is absolutely vital that you remember this. You follow the drill pipe pressure schedule, not your instinct about the casing gauge. Like we established earlier, the drill pipe gauge is your only truth. Well control kills people who trust the wrong gauge. It really proves that maintaining control of a highly volatile system often requires doing the exact opposite of what your gut is telling you to do.
To wrap up this explainer, let's hit the fundamental takeaways. What actually separates a contained kick from a total disaster? It really comes down to three things: utilizing adjustable back pressure to hold the well, obsessively watching the drill pipe pressure while entirely ignoring expected casing pressure spikes, and relying on redundant chokes to safely route that abrasive, high-velocity gas. The BOP might shut the well in, but the choke manifold and the crew operating it are what actually kill it.
I'll leave you with this provocative thought to chew on. If the absolute golden rule of well control requires you to actively fight your own human instinct to relieve pressure, what other safety systems on a drilling rig rely on entirely backwards, counterintuitive logic? It's a fascinating look at cognitive dissonance in engineering, and I highly encourage you to join us for our next explainer to find out. Keep learning, keep questioning, and I'll catch you next time.